Hello everybody, we are now in chapter 10, moment of inertia. Now I had uploaded a couple of videos from the internet trying to help explain what the moment of inertia is. And now what I'm going to go through is the calculation part. Hopefully you understand what that means. In class I try and give some examples by showing what it actually means, and hopefully those videos helped. So in order to calculate the moment of inertia, sometimes you call it the area moment of inertia or the moment inertia of an area. So first one we're going to look at is a rectangle. And if you notice that the rectangle, I have two different axes. So on the first one, the axis is from the actual centroid for the square and from the circle. So the centroid is showing both of those. So the moment of inertia of a rectangle is a simple formula. It's Ix is equal to, and we'll call this Ix prime. Ix prime is equal to BH cubed over 12. And Iy prime, the moment of inertia about the y-axis, is, we'll call this HB cubed over 12, where B is the width and H is the height. So this is your height and this is your width or your base. So that's how that is calculated. For a circle, again, you could use the back of the book. They give you the same exact equations. This is pi r to the fourth over 4, or you could say pi d to the fourth over 64, and Iy prime is pi r to the fourth over 4, or again pi d to the fourth over 4. Now again, this is if the axis is setting at the centroid. Now again, notice how this just swapped, right? The B and the H is just swapped. So if you would rotate this, it would be the same thing. You could say BH cubed. It's all depending on how you're orienting your axis and how you want to call this base and height. Now if I have my axis not at the centroid, my axis is somewhere off to the left. Here I'm saying that my axis is at this point here. My formula changes a little bit. Now I have Ix is equal to Ix prime. Now that's why I called this Ix prime, because it's just going to be the same exact BH cubed over 12, but I have to add the area times the height or the distance to the center of this object and how it's rotating about this axis. So I need this distance here is dy. So if I rotated this object, if you will, around the x-axis, I would need this distance of y and the area to notice how much moment of inertia I have about the x-axis. Now my Iy is Iy prime, which again, hb cubed over 12, plus a dx squared. Now my dx here is going to be this distance right here, dx. Again, now if I was to rotate this around, so think of me holding this plate right here. What kind of inertia would rotate around that axis? Now it would be a lot less here, right? If you have the axis about the centroid, it would be a lot less than over here. If you're rotating this thing around this axis here, you have all this area, all this distance rotating around the y-axis, and the same thing for the x-axis. So here, this is just the areas, and these are my dy's, the distance from the x-axis to the center, and dx there as well. Now for the circle, it would be the same exact anything. It would just be Ix is equal to Ix prime, which we note here, plus ADY squared. My IY is IY prime plus ADX squared. And just note, again, this would just be the radius, right? Or we could call this radius, or we could call this dy. For a circle, it's really easy, right? This is r is also my distance in x. So it's not a derivative or anything, it's just distance x. So I'm going to show a couple of examples. One example will be doing the moment of inertia about an axis over here, and then we're going to do one where I'm showing the axis over here. So if I gave you the axis that was here, but then I want you to find it about the centroid, you have to find the centroid first and then do the moment of inertia. So we're going to be doing two examples like those. Alright, thanks for listening.